Why waste time in commute and spend a lot of money for NEET UG coaching? Parents, do you want your kids to achieve top scores in NEET? India's leading online NEET coaching, 100% success. NEET UG. TeenEinstein.com. At TeenEinstein, we focus on NEET coaching from Class 6 to Class 12. We think you'll like it. Our teachers are mostly PhDs in physics, maths, chemistry, botany and zoology with lots of years of teaching experience for Class 6 to Class 12. Thousands of videos, quiz, MCQs. We provide a daily worksheet of 30 questions on each topic, math, physics, chemistry and biology for rigorous practice, concept understanding, evaluation, quizzes and thousands of videos. Limited offer, 40,000 per year. Book your class. TeenEinstein.com. Contact 99402 49720.
Hello everyone. In this video, we are going to continue talking about the moving charges and magnetism. In the last chapter itself, we studied that moving charges produces a magnetic field around them. So in this chapter, we are going to see what is Ampere's circuital law, the solenoid and the toroid. Then we will see the force between two parallel currents and how it defines the ampere. Then we will see torque on current loop, magnetic dipole, and then we will finally see the moving coil galvanometer. So what is Ampere's circuital law? So this Ampere's circuital law is similar to Gauss's law in the electric fields. So in Gauss's law, remember how we imagined a closed surface and we talked about how the charge enclosed in it decides how much is the force flux coming out of the surface. So here it is similar to that. In this we are going to consider an open surface with a boundary. So in this case, if this is the open surface but it has a boundary like this, closed boundary like this, and the surface has current passing through it. So through this surface there is a current passing through. So this I is the current that is passing through. So this is the boundary of the surface and this blue shaded region is the surface. This boundary is considered to be made up of a number of small elements with length dl. So we will just take this boundary and divide it into small line element each with length dl. So the tangential component of the magnetic field is Bt. This magnetic field is produced by the current that is flowing through here. So that magnetic field strength along the loop is now Bt. So if you want to calculate what is Bt in dl, then you can integrate it over the circuit, then you will get the overall tangential component multiplied with the length of this loop. So that's why we have this, and now that's why Bt dl is equal to B dot dl because it's a dot product, because it is B along the line, so it is a dot product. And then we have to add all these dot products, then we will get the overall B dot L. Now Ampere's law states that this integral is equal to mu 0 times the total current passing through the surface. So if you look at this formula, this is very similar to Gauss's law. In Gauss's law, we had in the left hand side electric flux and in the right hand side epsilon 0 and q by epsilon 0. In this case, instead of epsilon 0, we have mu 0, and instead of q, we have I. Because here current is the source of electric field. In that case, charge is the source of electric field. In this case, current is the source of magnetic field. That's why we have in the right hand side I. So what does this equation tell us? If you want to find out what is the magnetic field produced by this I, you have to imagine an Amperian loop. Then you see how much current is passing inside this. So how much current is enclosed. And that will be mu 0 I on the right hand side. That will be equal to B dot dl integral over a closed loop. So this is Ampere's law. And this loop is called Amperian loop, which can be chosen based on our problem, just like Gauss's surface, which based on the symmetry of the problem, we could choose any kind of Gaussian surface. Here also we can choose the Ampere's loop based on the symmetry of the problem. Okay, if L is the length of the loop for which B is tangential, let I be the current enclosed by the loop. According to Ampere's law, BL equal to mu 0 into I, because in the left hand side instead of B dot dl, we are replacing it with BL because L is the overall length. So if you take the dl's and add all of them, then finally you will get L being the length of the loop. Then you get BL equal to mu 0 I. When there is a symmetry associated with a system such as a straight infinite current carrying wire, Ampere's law enables easy evaluation of the magnetic field, just like Gauss's law. So imagine if you have an infinitely long current carrying wire, if you find the magnetic field in the traditional way, you have to take small elements and then find what is the final magnetic field. But instead of doing that, if you just draw an Amperian loop around it, just like how we did in Gauss's law, then you can easily calculate what is the magnetic field produced by this. So whenever there is a symmetry, Ampere's circuital law becomes very useful. For a circular loop, when the magnetic field is tangential to the circumference of the circle, the left-hand side of the equation becomes B dot 2 pi r. Why is this the case? If you have a circular loop, the length of the loop is going to be 2 pi r, that is the circumference of the loop. Then we have in the left-hand side B dot 2 pi r. In the right hand side, we have mu 0 into I. So in the left hand side, you have P multiplied by 2 pi r. In the right hand side, you have mu 0 I. So if you want to find the magnetic field, then magnetic field equal to mu 0 I by 2 pi r. Okay, so this is the equation for finding the magnetic field at a distance r from the current carrying wire, given that I is the current. So it implies that the field at every point on a circle of radius r is same in magnitude. The magnetic field possesses cylindrical symmetry. Just by looking at this equation, we can understand that for a constant current, the value of B depends only on r. So for example, if you have a straight current carrying wire, and if you see at equal distance r, that means in a cylindrical way, then the B is going to be same. So it has a cylindrical symmetry. So a current carrying wire has a cylindrical symmetry because B depends only on R other than I. If I is constant, then it depends only on R. So it has a cylindrical symmetry. The field direction at any point on the circle is tangential to it. The lines of constant magnitude of magnetic field form concentric circles. That is why the iron fillings form concentric circles when we put it in a paper, when there was a current flowing in or coming out of the paper. These lines are called magnetic field lines. They form closed loops. So this is very different from the electrostatic field lines. If you remember, electrostatic field lines always originated from positive charges and they ended at negative charges. But in this case, the magnetic field lines do not start from any point or go to any point. They form closed loops. So there is no origin or end for the magnetic field lines. The field is directly proportional to the current and inversely proportional to the distance from the current source. Okay.
Why waste time in commute and spend a lot of money for IIT JEE coaching? Parents, do you want your kids to achieve top scores in IIT JEE? India's leading online NEET coaching 100% success IIT JEE. At TeenEinstein, we focus on IIT JEE coaching from Class 6 to Class 12. We think you'll like it. Our teachers are mostly PhDs in physics, maths, chemistry, botany, and zoology, with lots of years of teaching experience for Class 6 to Class 12. Thousands of videos, quiz, MCQs. We provide a daily worksheet of 30 questions on each topic: math, physics, chemistry, and biology, for rigorous practice, concept understanding, evaluation, quiz, and thousands of videos. Limited offer 40,000 rupees per year. Book your class. TeenEinstein.com.